Okay, so where was I? I was here. Okay, so yes, if I remember correctly, I told you guys to do all questions from 1 through 14. So I just want to know if you have attempted those. Do you have any issues with any of these? Any questions about any of these? Okay.
I'll be back.
All right, let's see here. Okay, let me scroll down a bit. All right, I should have arranged this. Okay, I think I realized my. Okay, so for part B, this deals with what we call electron configuration. So basically, I don't remember if we covered this earlier, but
We did it.
no, not this,
No.
but something else that's kind of related. So in an atom, there are three main particles. You have the protons, the neutrons, and electrons. The protons and neutrons are located within the nucleus, while the electrons are basically surrounding the nucleus, right? They travel around the nucleus. So basically, the different elements will have different numbers of protons, right? So each element will have their own unique number of protons. And that number of protons is known as the atomic number, which you'll see in any periodic table, right? Now, in any atom, the number of protons and the number of electrons will be the same, right? So, for example, in the case of sodium, if you go to the periodic table, you'll see that sodium has an atomic number of 11, which means that the sodium atom has 11 protons and 11 electrons, all right? Now, what we're concerned about in part B is how the electrons are arranged in the atoms, right? And basically, the electrons are arranged in what are called shells. And let me just open up this here so I can explain in more detail what we're talking about here. So basically, in the first shell, you can imagine an atom consisting of, hold on. Okay, so you can imagine an atom consisting of a nucleus. The nucleus will have the number of protons and neutrons, right? And then we can use circles to represent the shells, even though it's not an accurate representation, but we can use the circles to represent the shells to say that the electrons are traveling within these orbits. And for all purposes, we're just concerned with the first four shells. There are more that can exist, but we won't go beyond the fourth shell, right? So that's what I'm drawing right here, right? And it turns out that each shell can have a maximum number of electrons, right? So for the first shell, we call this the n equal 1 shell, right? The maximum number of electrons it can have is 2, right? And I'm going to use arrows here to represent the 2 electrons, right? In the n equal 2 shell, the maximum number of electrons will be 8. And then in the third shell, the maximum number of electrons again is going to be 8. Right? And then finally, in the fourth shell, for all purposes, the maximum is going to be 2. Now, it can have more than 2, but for all purposes, we won't go beyond calcium, which is what this would represent, right? So what I'm showing you here is a maximum number of electrons that can occupy each shell, depending on, of course, the number of electrons that the atom will have, all right? So going to the assignment question, for example, sodium, as I said before, has an atomic number of 11, right? So, oh gosh, where is this thing? Okay, so sodium has an atomic number of 11, right? So I'm just going to create a column here, atomic number, right? So 11 would be for sodium, right? So as we said before, the first shell can have a maximum of 2 electrons, right? And then the next shell will have a maximum of 8 electrons. all right? And then finally, the third shell, because the total number of electrons will be 11, will have 1 electron. So therefore, that would be the electron configuration of sodium, right? So basically, you assign the electrons according to the different orbitals or shells, I should say, and keeping in mind which is the maximum number of electrons that the shell can occupy. And therefore, you end up with the electronic configuration, which is what this is for sodium, all right? Now, if I were to do the same thing for chlorine, again, you go to the periodic table and look up the atomic number of chlorine. And if you do that, you're going to see that it's 17, right? So you have 17 electrons to play with. The first 2 will go into the first shell. Then the next 8 will go into the second shell. So we have used up 10 so far of the 17 electrons, which means that the third shell will have 7 electrons. And that would be the electron configuration of chlorine. Okay, so let's see if you can do for magnesium. So if you go to the periodic table, you see that magnesium has an atomic number of 12, right? So how many electrons will go into the first shell? Remember, the maximum number of electrons that can go into the first shell is 2. The maximum that can go into the second shell is 8. The maximum that can go into the third shell is 8. And then in the fourth shell, it's 2. So what's the maximum number of electrons that would go into the first shell? Same as here and here, right? 2, right? What's the maximum number of electrons that can go into the second shell? Okay, so we have used up 10 so far. So what does that mean for the third shell? How many electrons will end up in there? We have used up 10 of the 12, which means that you're going to have 2 electrons here left in the third shell, right? Okay, what about nitrogen? Now, the atomic number of nitrogen is 7, all right? So how many electrons are going to the first shell? And then how many electrons are going to the second shell? Nope. Remember, the atomic number is 7. 5, exactly. Okay, what about the silicon? I don't remember. The atomic number of silicon, hold on. No, let me not try.
14.
14, that sounds about right, yeah. Okay, so in the case of silicon, we have 14 electrons to assign. So how many will go into the first shell? 2. How many will go into the second shell? No,
12.
no. Remember, the maximum number in the second shell is 8, right? So what does that mean for the third shell?
6.
What's the atomic number of silicon? Silicon is 14, right? So that means that how many electrons you're going to end up with here?
4.
Exactly. All right. And then finally, or maybe I spoke too soon. Hold on, let me.
No, there's.
Oh, we have several more. Okay. Aluminum. Now, if I remember correctly, aluminum has an atomic number of 13. Right? So if aluminum is 13, then how many electrons go into the first shell? 2. And then the second shell? The maximum number of electrons that can go in the second shell is what?
8.
8. And then what? Remember now, it's 13 electrons. 3, exactly. Okay. What about carbon? Now, carbon has an atomic number of 6. So how many electrons in the first shell? 2. How many in the second shell? 4. Exactly. And that gives you the total, right? Fluorine. Now, fluorine is, the atomic number is 9. So first shell will contain 2, and the second shell will contain Nope. Remember, 9 is the total.
8,
Nope.
or it's gonna have 7.
7, exactly. 7 plus 2, 9. All right. Phosphorus. No, phosphorus, if I remember correctly, is 15.
That's why fluorine is so volatile, because it's right there.
I'm sorry?
Fluorine is so volatile because it's just right there.
Oh, yeah. Mm-hmm.
Yeah.
Phosphorus, I think the atomic number is 15. So how many electrons in the first shell?
2.
2. And then the second shell? 8. And then the third shell? 5, exactly. And then finally in this list, boron. I forgot, I think it's 5. Can somebody confirm that? Atomic number of boron is 5.
5.
Okay, good. So the first shell will contain 2 and the next shell will contain 3, and that's it. All right, so that's how you show how the electrons are distributed among the shell. All right, so if you understand that, then, oops, you should be able to, as soon as I clear this, you should be able to do these down here, right? So in this case, and the first one is worked out for you so that you'll understand how to do the others, right? You have to go and consult the periodic table to find out the atomic number, and then you're going to determine how the electrons are distributed among the shells, right? So like in this case here, the atomic number of oxygen is 8, which means that it has 8 electrons. And then you start distributing the electrons. So the first 2 would go in the first shell, and then the rest will go into the second shell, and that's it, all right? So let's look at sodium. So I need you to look up the atomic number of sodium. Okay, so what's the atomic number of sodium? Anybody?
11.
11. Okay, so how would we determine the electron configuration?
2.
2? Yes, ma'am.
Can I have a piece of the paper?
I don't have any copies of it, I'm sorry. But didn't I give you guys a copy last week?
Yeah.
Yeah, I don't know if you weren't here?
No, I was here. I just didn't know we were still working on the same piece of paper.
Yeah. Yeah, we're still working on this. Okay, what was I saying? Okay, so the first 2 electrons go into the first shell, and then what? How many electrons will go into the second shell?
8.
8, exactly, because that's the maximum number of electrons that can go into the second shell, right? And then the next shell will contain what? 1, and that's it. Okay. So that's for sodium, all right? What about sulfur? What's the atomic number of sulfur? Again, I need your help. You have to look it up. Or
16.
16, okay. So first shell will contain 2. The second shell will contain 8. And then the third shell will contain, sure about that?
6.
6, right? Because remember the total is 16. 2 and 8 is 10. That means that the next shell will contain 6. All right. I'm assuming that you have this written down, right? Can I clear this? All right, clear this. Okay, the next one, potassium. Okay, so what's the atomic number of potassium?
9.
19. And then let's go into the configuration. So the first shell would have what? 2. The next shell would have
8.
8. The next shell would have no. The maximum number of electrons in the third shell is 8, just like in the second shell.
9.
So this will be 8 right here, right? So that's 10 plus 8, that's 18. So that means that?
9. There's 1.
Exactly. And that's the electron configuration for potassium. So remember, first shell can have a maximum of 2. The second and third shell each will have a maximum of 8. And the last shell, for all purposes, will have 2, even though it can have more, but we're just stopping at 2 in that case, all right? Aluminum. What's the atomic number of aluminum? 13. Okay, so how do we distribute the electrons? The first shell would have how many?
2,
Two. The next shell would have
8,
eight. And then the third shell would have
3,
three. And that's it. Okay, chlorine. What's the atomic number of chlorine? 17. So the first shell would have 2. The next shell would have
8,
8. And then the third shell would have
7,
7. And that's it. Calcium. What's the atomic number of calcium? 20. All right, so first shell would have 2. Next shell would have 8. The third shell would have maximum number in the third shell would be 8. It cannot have more than 8 electrons in the third shell. Just like the second shell, the maximum would be 8. So this would have to be 8, right? Which means that in the fourth shell, 2, right? So basically, for all purposes, we're stopping at calcium in the periodic table. We won't go beyond calcium, all right? Even though we can, but things are a bit more complicated in terms of electronic configuration. So I only do that when it comes to like my introductory chemistry or general chemistry, but not for this course. Okay. Fluorine. The atomic number of fluorine is 9. I remember that. So what's the electronic configuration? 2,
7,
7, and that's it. Okay, very good. Nitrogen. The atomic number of nitrogen is 7. Yeah, that sounds about right. So the first shell will contain 2 electrons, and the next shell will contain.
Wait, you said we weren't gonna go beyond.
No, he meant.
Okay, I guess it goes more in the shells.
So for nitrogen, what's the next? What goes here? Second shell.
5.
5, and that's it. Okay, now I just realized this. That's an error on my part
It's 53.
because iodine is 53. We're not going that far at this level. Let me clear this here. So you can scratch out iodine. Is there any more?
No.
Oh, that's it. Okay. All right. So that's basically how you determine the electron configurations for different atoms. As I said before, we won't go beyond 20 electrons, which is calcium. All right. Okay. Now the next thing I want to talk about, and that once we cover this, this will be pretty much all for today. The next thing I want to talk about is what we call Lewis structures. All right. Lewis structures is basically a representation of how we put together molecules or put together atoms to form molecules. All right. So I'm just perusing what we have here so that I can figure out how to introduce this to you guys. Okay. So basically, there are several steps involved when it comes to determining the Lewis structure of a compound. And the best way to learn this, in my opinion, is to go directly to some examples, right? So just let me give a simple example. This here is the Lewis structure of the water molecule. All right? So let me just explain what we're talking about here. So water, of course, is H2O. What we're concerned with is how the atoms are connected to each other, right? So in this representation, you have the oxygen, which is simultaneously bonded to 2 hydrogen atoms, all right? Now, each of these lines represents a shared pair of electrons, right? We call these covalent bonds, right? And these bonds are basically a shared pair of electrons, all right? So basically, each of these lines represent 2 electrons. In fact, another way of representing it is this. All right. So you can use 2 dots representing 2 electrons, or you can use lines, but you have to remember that each line represents 2 electrons, right? So this line represents 2 electrons being shared between the oxygen and hydrogen, and the same is true for that line right there, all right? Now, we call these pairs of electrons that are involved in bonding. We call them bonding pairs. Bonding pairs of electrons, all right? Now, that's important because there's another type of pair of electrons that you'll find, and these are called lone pairs. That's these electrons right here. These electrons are not shared between atoms, right? So we call these lone pairs of electrons, all right? So in pretty much all Lewis structures, you're going to have bonding pairs, but you may have some lone pairs of electrons, all right? And this will become important when you look at, for example, shapes of molecules and so on. But before we get to that, we have to understand how do we determine or draw Lewis structures, all right? So I just did this example just to show you, what a Lewis structure looks like and what are the bonding pairs and lone pairs, all right? So let me, another thing I want to mention too is that for all atoms excepting hydrogen, the atoms will try to end up with 8 electrons on its outer shell or as bonding and lone pairs, right? So in the case of this oxygen right here, right? If you look at this oxygen, it has 2, 4, 6, 8 electrons, all right? Most atoms will try to obtain 8 electrons. In fact, the one exception that won't have 8 electrons would be hydrogen. Hydrogen cannot have more than 2 electrons, all right? So if you look at this hydrogen here, it has 2 electrons shared with the oxygen here, and this hydrogen has 2 electrons, right? So hydrogen is a bit of an exception, but pretty much all other atoms that we're going to meet will end up with 8 electrons. And the term that we use in chemistry, we say that the atom will obtain an octet of electrons, right? So when you hear the term octet, that's referring to 8 electrons, all right? Okay, so I thought I should cover all that so we can look at some examples. So let's say you're asked to draw the Lewis structure for ammonia, which has the formula NH3, all right? So you're to draw the Lewis structure of this molecule, all right? Now, the first step in this process is that you count up what we call the number of valence electrons, and these are the electrons that will be involved in bonding. So you might be wondering, how do we determine the valence electrons? Well, that's very easy. All you have to do is consult the periodic table and look up the group number for the different elements involved, right? So if you consult the periodic table, you'll see that nitrogen will have a group number 5, so therefore it will have 5 valence electrons, all right? And then if you look up hydrogen, hydrogen will be in group 1, so therefore it will contribute 1 valence electron. However, because you have a 3 here, right, you have 3 hydrogens, that means that collectively they will contribute 3 valence electrons. So therefore, the total number of valence electrons will be equal to 8, all right? Now, what I like to do when I get to this stage is that I like to look at the electrons in terms of pairs, right? So I would just say that this would be equal to 4 pairs of valence electrons, all right? And then what I would do next is put nitrogen in the middle of the structure and surround it with the hydrogens, like this, all right? And then what I would do is assign the bonding pairs first. Now we have 8 electrons to work with, or 4 pairs, right? So what I would do is that I would put 1 pair between this nitrogen and this hydrogen, another pair between this nitrogen and this hydrogen, and a 3rd pair here, right? So I've used up 3 of the 4 pairs. Now the question is, where will the 4th pair end up? Well, typically you put the 4th pair on the atoms surrounding the central atom. However, you cannot do that for nitrogen. I'm sorry, you cannot do that for hydrogen, because hydrogen can only have 2 electrons, right, on its outer shell, right? So therefore, that means that those 2 electrons you'd have to place on the nitrogen like that, and this would be the final answer. This would be the Lewis structure of ammonia, all right? So that's basically how you would do that. All right, any questions? Any questions? Okay, let me do another one. Suppose you're given,
Wait, so we're supposed
oh, sorry, what's that?
We're supposed to add up the group number.
Exactly, but in the case of hydrogen, because you have three hydrogens, you have to multiply that by three,
Yes.
and then you add them up, and then you move on to the next step. Okay, so let's see here. See if I can come up with another good example. Let's say you're given. Okay, let's say you're given SCl2, all right? So you're asked to do the same thing. You're asked to draw the Lewis structure. So again, you'll go to the periodic table and you look up the group number for sulfur, right? And if you look it up, you see that it's 6. And then you look up the group number for chlorine and you see that it is 7. But because you have 2 chlorine atoms, you have to multiply that by 2. So that gives you 14. So the total number of electrons here would be 20 electrons, all right? Then we put the sulfur in the middle and the chlorines around it. And then we start by putting the bonding pairs first, right? So one pair would go here and one pair would go here, right? So we have used up 2 of the 20 electrons. Oh, by the way, I forgot. This can be seen as 10 pairs. I like to look at them in terms of pairs, all right? So we have used up 2 of the 10 pairs of electrons, right? So the question now becomes, where will you place the other pairs? The other pairs, you start adding them to the atoms bonded to the sulfur. So this is pair number 3. Oops, sorry. So this would be pair number 3, 4, 5, 6, 7, 8. All right, so now we have used up 8 of the 10 pairs. So the next question is, where will the other 2 pairs end up? And the answer would simply be on the sulfur. And that's it. And that would be the Lewis structure of this molecule. All right. So, so that's it. Let me just say that you should notice that in each case, each atom will end up with an octet. Remember I mentioned that in most of these molecules, the different atoms will have 8 electrons. So if you look at the chlorine here, this chlorine has 2, 4, 6, 8 electrons, 3 non-bonding pairs, 1 lone pair. The same is true for this chlorine. And then for the sulfur in the middle, you have 2 bonding pairs and 2 lone pairs. So that's a total of 8 electrons surrounding the sulfur as well. And that's pretty much it as far as the Lewis structure of this molecule is concerned. All right. Okay. Any questions about this one? Any questions? Okay, so let me give another example, and this time I want you to tell me how you tackle this one. Suppose you're given, okay, suppose you're given CCl4, all right? So what would be the first step, based on what we did before? The first step would be what? What would be the first step?
You would have to find the group number.
Okay, so what's the group number for carbon?
14.
Nope. Carbon, you sure about that?
I mean,
Look at the periodic table.
looking at the periodic table, it is 14.
Okay, that's one version of the periodic table I think you're looking at. Hold on.
It's. Wait, are we
6 carbon.
6?
No, not the atomic number, the group number.
Oh.
Let me see if I can bring up the periodic table here.
14. The group 14.
Okay, I think I understand. I think I know what's happening here. Hold on. Okay, so if you look at this periodic table here, there are 2 numbering systems. The numbering system that we use to determine the group number for our purposes for these problems would be the 1A, the 2A, 3A, and in the case of carbon, that would be 4A. So 4 would be the group number that we'll be using, not 14. All right? So going back to the problem, sorry. We would say that the atomic number of carbon is 4. And then in the case of chlorine, the atomic number would be 7. Let me go back to the periodic table here. Here, chlorine is in group 7A. So 7 is the number that we're going to use. So we're going to put 7, but now we have 4 chlorines, right? So that means we need to multiply this by 4. So this gives us 28. So the grand total would be 28 plus 4, which would be 32 electrons, which would be equal to 16 pairs. All right? So we put the carbon in the middle and surround it with the chlorines. And then we put the bonding pairs, 1, 2, 3, 4. So I've used up 4 of the 16. Then 5, 6, keep using, okay, I'll explain why I keep doing that. Yes, ma'am.
How did you get 16?
Because the grand total is 30, whoops. Accidentally erased it. 7, 4 is 28, right? 28 plus 4 is 32 electrons, which is 16 pairs. You just divide by 2 and you get the number of pairs, right? So we have used up 4 of the 16 pairs here as bonding pairs. Then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So I've used up all the pairs of electrons, and therefore that would be the Lewis structure for this compound. And let me just say this. There's another way which I did not mention in terms of representing the Lewis structure, specifically as it relates to the non-bonding pairs, right? So I'm just going to draw this representation here. Right? Now in this representation, each of these lines here represents a lone pair of electrons or a non-bonding pair of electrons. Here, here, and so on throughout the structure. So these two are the same, all right? So that's basically how that is done. Okay, so with any questions before I move on? Any questions? Any questions? Okay, so what I want you to do now are the problems in that handout, starting with question number 1 in part C. So I want you to work on that. Now, if you have any questions, feel free to ask. Mhm.
Did you get, my, email for, in Canvas for, assignment 2? Cause I told you I turned it in late. And, I turned it in on time, but it wasn't through the proper thing.
Hold on 1 minute. What's your last name?
Warriors.
David?
Yes.
Oh, okay. Yeah, I think I have it. I haven't graded it yet though.
Okay.
Yeah. Okay, I'm gonna stop here for today. So, for those who came in late, I said to the group earlier that if you have not done the first test yet, today is the last day for you to do it. So if you can get that done, then that would be good. As far as this is concerned, this assignment is concerned, I just set up a Dropbox for the assignment to be due on, the 2nd of October, which is Thursday, if I'm not mistaken. Yes, Thursday. So you can submit it then. Also, make sure you watch the videos that I've published based on chapter 4. And I would strongly recommend that you watch it carefully, the different links, because it's dealing with a topic which is kind of important, dealing with nomenclature, which basically deals with the rules for naming compounds, right? So that's pretty much it, unless you have any questions you want to ask. Any questions? Okay,
Tonight,
I'm sorry?
traffic is due tonight.
No, it's due on Thursday.
Oh.